Hello, everybody. Can you hear us? I think you can. Excellent. I'm just setting up the video and the audio. Just hang on one second. Yep, perfect. Looks like we're all good to go. Welcome to our webinar on PD case studies. With me today, I have Thomas Whyte, one of our field services engineers, and my name is Brad Monaghan, and I'm the head of services here in Brisbane. We've got an office in Brisbane, Australia, and that's where we're broadcasting from today. Nice sunny day outside. It's 10:30 a.m. where we are at the moment. We've got people logged in from all over the world here to listen to our webinar and watch us, and hopefully everybody will learn some stuff today. Okay, so the contents of what we're going to do today is we're going to go through why we test for PD. We're going to go over a summary of the PD classifications and the techniques we use to detect different types of PD. And then we're going to go through 4 case studies. So we're going to do one on cable PD, switchgear PD, some 24/7 PD monitoring, a real life situation that occurred and the problems that happened around that, the steps taken, and then we're also going to just do one on UHF, namely our directional UHF antenna. Thomas will take you through the first 3 case studies, and then I will do the last one and a bit of a summary at the end. So if anyone has any questions or they want to make any comments, there's a little orange tab, a little orange arrow, sorry, in your software there. If you click on that, it should open up a bunch of options, I believe, and there'll be a questions box there. And if you type any questions in, we will either get back to you via typing here. We can answer you in real time. I might ask Thomas or myself can answer via voice while we're all talking. Or we might, if we don't know the answer or it's a pretty big question, we'll get back to you after this because we can answer you via email. And we also know a few of the people that are logged in anyway, so we can contact you direct via phone if you'd like. Either way, it does not matter. So let's get started. So why do we test for PD? So if we're testing for PD, we are looking for your high voltage insulation system breaking down over time. What tends to happen is when PD is occurring, it will occur for a certain amount of time before a failure occurs, and that might be days, weeks, months, years type thing. And so what we're trying to do is use our online testing techniques and a proper program of testing to capture those defects before they become a failure. Okay, so obviously failures are a big risk, a big explosion, a big production shutdown, a big money cost to businesses, but there's also a high voltage explosion. So what it will do is it will increase your safety. It'll increase the safety to your workers, the people that are working around your high voltage assets, with your high voltage assets, the safety of the general public that are nearby. It'll improve the asset performance because it'll last longer, it hasn't had a failure, and it will give you a financial benefit because you'll be able to spend money on things that have problems rather than spending money on everything broadly where there may not be problems. So you can make better investment decisions with that money. PD is a factor in around 85% of unexpected substation failures. So it is a very, very, very good test to run on your high voltage assets to see what condition it's in and you know, pick it up before failure. And that's what it's all about. Okay, a summary of the PD classifications and the techniques we use to test for discharge activity. Okay, so there's 3 main classifications of PD. The first one is internal discharge. This is where you've got PD occurring on the inside of insulation systems, on the inside of your high voltage asset or insulation. And that'll be caused by some sort of defect. The defect can be there through workmanship, installation, deterioration. It can be there from manufacturing. It'll be some sort of split or void or air bubble or something that shouldn't be there, which basically can't hold the bolts in that are put across it. It'll discharge at a certain voltage level, and it will start to arc and spark across this gap. When that occurs, it can eat away through your insulation system and eventually bridge out your electrodes, that being phase to earth or phase to phase, and cause the HV failure. The second one is surface discharge. So surface discharge is when you've got PD activity happening on the outside of your insulation system, and that will be caused by sharp points or defects on the insulation itself, and it can also be caused by things of another voltage that are close to your insulation, and there's basically the clearances are too small and you get a build-up of PD across that gap. Common ones for that are, say, earth straps too close to cable terminations, or the cable terminations being too close to each other themselves. It can be bus bars going through barrier boards inside switchgear. It can be a whole range of things, but when something's too close to your HV insulation, you can have a build-up there of discharge. And the third one is corona. Corona is from a physical sharp point into a gas. So the easiest way to find corona is to go out into a noisy switchyard on a misty morning or a high humidity day, and you hear a lot of buzzing and arcing and all that sort of stuff going on. You go back in the afternoon and you can't hear it buzzing and arcing, and that's because the humidity's dropped and there's not as much moisture in the air. But a lot of that buzzing and arcing will be coming from sharp points just due to the physical construction of things, of your assets, and it's discharging from that point into a gas. When it's in an outdoor switchyard, it's generally not a problem because there's basically airflow at that point, blowing away all the chemical reaction that's occurring. But if you have corona on the inside of switchgear, it usually is a problem because it will create gases such as ozone that'll mix with moisture in the air and produce nitrous oxides and nitric acids and start to eat away at things in those chambers. Then we have, sometimes it's not that simple. Sometimes we have an intermediate state between surface and internal where we have sparks jumping across a gap. Classic one for this is if you have a poor high voltage connection. So just say you had two conductors that are meant to be bolted together. If they're not bolted together, there's a gap there and you can have sparks jumping across that gap. Another one in that realm is what we call floating metal work, and it's not so much a problem, but it does create a lot of PD signals that we can detect, and that's where we have basically pieces of metal really, really close to your high voltage assets that have an induced voltage on that piece of metal, and that piece of metal is a different voltage to the next piece of metal and to the next piece of metal, and you have tiny little you have an interaction between those pieces of metal, and they can cause issues for you as well in terms of giving you signals. The last one is when we can have surface and corona occurring at the same time, and that's when a lot of things start out as corona. There'll be a sharp point or some sort of defect on your insulation or at the edges of your insulation, and it will start out as corona. And once that starts, it can mix with or produce ozone and do the nitrous oxides and the nitric acid, as I said before, and turn into basically surface activity and surface tracking. So you can have a few things going on at the one location. Okay. But we know how to detect all of those situations, and what we have here is 4 main test methods that we use and that EA technology instruments use to detect them. So the first one is TEV. What TEV stands for is transient earth voltages. The easiest way to explain transient earth voltages is a tiny little voltage that appears on the outside of your switchboard or your high voltage cable because of PD that's occurring on the inside of your switchboard or your high voltage cable or you know, whatever the asset may be. The way to detect the TEV signals is simply to get an ultra TEV +2. It doesn't have to be an ultra TEV +2. It can be one of the older instruments or a monitor. It doesn't really matter. But what you need is physically there's a TEV plate behind here. You put that onto the outside of the switchboard. Just pretend my phone is the switchboard. Put that on the outside of the switchboard, and this instrument will detect those tiny little voltages. It will put it on that screen, and then the analyst, such as the PD surveyor, the user, can then go from there and figure out if you're detecting PD. The second way that we detect, firstly, TEV signals are more inherent with internal void PD. So when we have internal void, the best way to detect them is TEV. Then when we have surface activity and surface tracking, in that instance, we use what we call ultrasonic sensors, ultrasonic microphones, where we're listening for PD just with a basic microphone that's listening at 40 kilohertz. It's listening where humans can't hear. Humans can only hear up to 20 kilohertz. And we listen into all the chambers and listen for arcing and sparking and crackling and all that sort of stuff going on. So your corona, your surface tracking, and when sparks are jumping across a gap can get picked up with ultrasonic. The third one is using an RFCT or a HFCT to detect high frequency current pulses that are produced by cable discharges. I've just had a question come through. What's the difference between an RFCT and a HFCT? The answer is it's basically just the letter at the start. RFCTs and HFCTs do the exact same thing. Thomas has one here. It's just in the naming convention. Originally they were called radio frequency CTs, and now we're calling them high frequency CTs because it's just a lot more common to call them HFCTs. One just stands for radio frequency and one stands for high frequency, and I believe there's an overlap in those basically those frequency ranges, the frequency bands. Yep. So that's another way to detect. And then the fourth way is to look for UHF signals. The best way to look for UHF signals is to use an antenna, and that antenna will detect basically UHF signals that are being broadcast by a PD, by a discharge that's occurring. Okay. Here we have a list of 4 different types of high voltage equipment and what test is, the best way to detect those signals coming from those if there is discharge in those assets. So the first one is if you've got enclosed switchgear such as metal clad switchgear, ring main units, kiosk substations, anywhere where there's high voltage equipment inside big metal boxes, the best way to detect the PD signals from there is TEV and ultrasonic. Now, when we go outside into the outdoor yards and when we're looking out in the streets where you've got overhead assets, out in switch yards, or where you've got ring main units where you can see all the exposed high voltage equipment. Again, TEV and ultrasonic are very, very good, but we can also use the UHF antennas to detect for PD at those locations. Now, cable terminations. When we have cable terminations, that can either be on transformers or switchgear or wherever those cable terminations are. Again, we can use TEV for looking for the internal stuff, ultrasonic for looking for surface tracking. When those terminations are exposed, as in you've got a direct line of sight between you and it, we can use UHF antennas, and we can also use HFCTs if you can clip them around the screens of those cables. Now, underground high voltage cable circuits, we can use TEV, the HFCT, or we can use the UHF antenna if we have a clear line of sight to that type of asset. Okay, so now I'm going to pass over to Thomas for our first 3 case studies, and then I'll do one after that.
Thank you, Brad.
Go for it.
So our first case study we're going to go through today is on cable PD and how we managed it all the way through from the initial testing, what processes to do, all the way through to a HV failure. So this one comes from a big client of ours, a major gas-fired power plant, and they have quite a large HV network, and they approached us because they were quite worried about their underground cables. So we discussed with them the best thing they could do to condition monitor their cables online was to use our cable data collector. This uses the implementation of the HFCTs, and you attach them around the earth screens of your cables. The biggest problem they faced was actually that their earth screens were not accessible. So in order for them to do this testing, they needed to take an outage, attach the HFCTs, re-energize, and then do the test. Because that's quite a difficult process, what they decided to do rather than taking an outage, installing them, and re-energizing, doing the test, and doing that for every single time, they decided the best option would be to permanently install these the HFCTs inside the HV chambers. What this allowed them to do was put the sensors inside, then run BNC cables out to the user in a safe location. They did this on a trial of 20 different cables, and they did periodic testing of a big sweep throughout the entire site. This particular client chose not to analyze the data themselves, but to send it back to us, and we then did the analysis for them. And this is what we get from the data. So on the right, you can see the data that our cable data collector gives us. So on the top right here, you can see the PRPD pattern, which gives us an amplitude in relation to the 50 Hertz sine wave in this case. So when I look at this, we can see two distinct clusters of activity with 180 degrees separation. So this cluster here is 180 degrees separated to this cluster here. And that is a telltale sign that PD is present. If we do look at these, you see they've got a wave-like effect, which indicates to us here that there's an internal void type problem present somewhere on this cable. And if we start to look at the amplitude of the signal, you may be able to see, but it's up at 4,000 picocoulombs, which if we do look at our matrices and our charts, puts it into the high level PD scenario based on the type of cable this is. So once we have established there was some sort of PD present on the cable, we start to do the time before the TDR process to determine the distance to fault. And that's what we use our middle pot for here. So this pot works quite well and it's very simplistic to use, but you basically define it as these three lines. The red line at the front indicates the test site. So it's the initial PD pulse hitting your test equipment to symbolize where you are on the test site. The end pulse in green symbolizes the far end of the cable, so the far end terminations, and that's where the PD reflections are bouncing off. The middle pulse in yellow represents the PD source itself. And by combining these three with some cable data, such as the cable type and the cable length, we're actually able to determine the distance that these pulses travel and determine the source of the defect. And in this particular scenario, it came out to be 69% down the cable from the test end. Looking back at the cable data, this was a 640 meter cable, and we were then able to determine that 441 meters down the cable, there was an issue. Traditionally, we would then go to the far end of this cable and perform the exact same test. In that scenario, what I'd expecting to see is a very similar phase plot, possibly at higher amplitudes because you'd be closer to the source at that point. But the waveform would show you the opposite of what we're seeing here. Rather than the source being at 69% down the cable, from the far end, you'd be expecting to see it at 31% down the cable. And these two numbers should correlate to pinpoint a single location of the PD source. We were then able to use the client's cable data to determine that where we were saying there was a defect at this 441 meter mark, there was actually a joint located at the same location. So this is a joint from a PILT cable to an XLPE cable. And based on what cables you are using and where and what component the PD source in, it actually affects the amount, what level amplitude puts it into different thresholds. So for this type of joint and this threshold, it's actually a red level, a high tier PD source. We then went through the client, what their moves could be. Naturally, the best option in this scenario would be to remove the joint and put in two separate joints and totally remove the PD source. Unfortunately for them, that this just wasn't an option. So their other options were continue periodic testing, see if that you can trend this PD source to see if it is increasing or changing in behavior, possibly giving you an indication that it is leading to failure. The third option was to install 24/7 monitoring. So the same sensors that they had already previously installed inside their HV chambers could be used to provide 24/7 monitoring with the data backed up to the cloud. This would allow them to keep a very close eye on it and put alarm thresholds on it so they would know exactly what is happening at every time. In this scenario, the client was actually happy to leave it as it is and continue periodic testing. This allowed them to be prepared for a failure and move on. 4 years after this test did take place, a HV failure did finally occur. This HV failure did result in an outage, but because the client was prepared for it, they had the spare parts, they had the spare cable ready, and they had a fairly good idea where that failure would occur. They were able to locate it quickly, replace it, and get everything back in service with as minimal interruption as they could. Because of this, they have actually now chosen to use this type of online testing with the permanently installed HFCTs as their preferred test method. So with all newly installed assets, they are actually installing these HFCTs onto the cables so they can continue this testing moving forward. But it's just a great example of having the knowledge and knowing the condition of your assets can really help you if something does eventually lead to failure. Our next example is on Switchgear PD, in particular, internal void PD. So we were on site at this particular board doing a handheld survey using the UltraTev Plus 2 in preparation for installing permanent monitoring. So whenever we install a permanent monitoring system, we will always do a handheld survey beforehand. And it really just helps you pinpoint exactly what assets and what components you need to focus all of your sensors on to get the best value. This particular gear was actually 1970s Westinghouse Rosebery 1110 kV switchgear. And the reason we were there is it was mostly pitch field bus and cable boxes, which the client had identified as a risk to their network. What we had found originally was we went along the front of the board and we found lots of different issues. The board had multiple PD defects that we were picking up. On the front of the circuit breakers, we found a localized high on one panel, and then as we moved around to the rear of the board, we found that higher levels on one particular cable box. But due to the amount of PD sources present on the board, it was quite hard to localize. So that's where we started to use the UltraTev locator and its time of flight functionality. We were able to test from cable box to cable box on both sides of where we suspected the source was originating, and the locator told us which probe was seeing it first. This allowed us to pinpoint it to a single cable box, or first to a single panel and then to the cable box on that panel. From there, we were able to use the time of flight functionality on the cable itself. So you could put both of your TEV probes on the cable, and what this allowed us to do was to determine if the PD source was coming from the switchgear itself or if it was emanating up from the cable and being induced onto the switchgear where we were testing. In this test, we were then able to determine that it was coming from this cable box right here. When we look at the phase resolve pattern for this, you can see multiple different PD sources. The most pressing one was this cluster here, or these two clusters, up at around the 30 to 40 dB mark, a high level TEV source. But not only that, is at the bottom you can see multiple different TEV PD sources, all in different phases. And we can tell that due to the separation of these patterns across the 360 degrees of the sine wave. So this was, we determined it came from a single cable box and it was a high level source. The really interesting thing about this particular PD source is we determined that it was an internal void type, so it came from a defect. We actually believe that at the trifurcation of that cable inside the cable box, when they poured in the pitch, there were either multiple air bubbles or voids or cracks, something that was causing this, the electromagnetic fields to focus on and the PD to occur. What is unusual is that we were actually also able to detect this source ultrasonically. So for internal void type PD sources, normally you cannot hear them ultrasonically because the sound is trapped within that void. However, on this particular source, we could put the contact probe ultrasonic sensor directly where this arrow is pointing here. And in that location, we could hear that kind of arcing sound, that deep crackling that is associated with PD. Then if you look at the phase plot, again, we see those two clusters of activities with 180 degrees separation, which indicates that there is PD present. So what I believe is that inside this pitch here, there is some sort of crack or some sort of defect extending out from those voids, which is allowing those sound waves to travel out, hit the metalwork, and that's how we can detect it. So with this particular source, we talked with the client, we told them it's a high level source, we've localized it to a single panel on this board, it's a pitch filled cable box, and we can detect it not only with TEV, but with ultrasonic. That client then decided that as these are considered to be a higher risk on their network, that they would actually de-energize the panel. They organised that about 2 weeks later, and due to the fact we just installed monitoring equipment on this board, we could actually see the second that they de-energized the panel, all PD sources disappeared from that panel, and the entire site became a lot quieter. Our third example is on PD monitoring, so real life alerts and what we do in real time when these things occur. So similar to the board we just looked at, we'd set up a full PD monitoring system. So it consists of a hub, which is out of frame in this picture, but then all of these blue nodes, which daisy chain along the board and magnetically attach. Into these nodes, we then plug in all the multiple sensors that then monitor the board itself. In this particular case, we've got an ultrasonic probe here listening into this cable box. This is only a small part of the larger system, and I think we were monitoring it for about 3 months and there was absolutely no activity being picked up by this sensor at all. Then one day, we saw a sudden increase in activity on that ultrasonic sensor. So you can see normally down here, you're reading between 0 and 3 decibel microvolts. Then suddenly there was an increase, it spiked up and then kind of plateaued down at about 10 dB microvolts. So this is an average sample reading over a 2-minute period, so it's very consistent. So when this event here happened, it triggered an alarm event. We were able to log in, analyze the data, listen to the ultrasonic sound file, and determine we believed it was genuine PD. We were able to quickly contact the client and ask them to attend site to perform a survey on the same area with the UltraTev +2 to confirm that the PD source is present. So our client, similar to down here, used the flexible sensor and the +2, and they actually recorded this phase plot here. And similarly, you can see it sitting at around the 10 dB mark, and you can see these 2 clusters of activity with 180-degree separation. So this phase plot is directly agreeing with what we saw on the UltraTev monitor system. Once again, we discussed it with our client, and on their matrix for their company, this 10 dB source was not considered to be a high tier issue. So rather than doing an immediate shutdown to find and fix the issue, they actually planned a shutdown for 2 months later. So 2 months later, they're actually able to de-energize and open up the cable box. And what you can see here is that these 2 phases were just a little bit too close and encroaching on each other's clearances. Therefore, you can see that build up due to the electrical interaction, and you can actually see a bit of dark burning starting to occur where the 2 phases were interacting with one another. So when they did this, they opened it up. It was a very simple fix. It wasn't catastrophic, and it wasn't to the point where they needed to re-terminate yet, because they got to it within a short period of time. If this was left for a number of months, number of years, there is a high chance that it would have eventually led to a failure with an outage. But in the bottom here, you can actually see this is our standard readings going along as the source was present. Then we hit the day 2 months later after the source was initially found. They de-energized, did the repair work and re-energized, and the source has not occurred since that day. So this shows how the full-time monitoring can pick up the inception of the new PD sources right as they occur, and it can take something that could have been quite a catastrophic failure and make it into a simple cleaning job and increase the clearance. Therefore, you're saving a lot of time and a lot of money in the long run with that one. I'll now pass back to Bad to run us through the last one.
Bad or Brad?
Bad.
No worries. I might just swap spots.
Yep.
Steve's just asked me a question. I'm just gonna say a lot of the time visually. Once you can get to it. Here's the mouse for that.
Thank you.
Okay, we've got one last case study here, and this is UHF signals on switchgear. So this one here is a ring main unit. This is a very old ring main unit made by a company called Hazelmeyer many years ago, and it's an open type construction where you've got, you know, you can sort of see where all the cables are, you can see where all the high voltage fuses plug in, and you can see all your switchgear, and it's quite open. In those instances, if there is PD, the UHF signals have got a really good chance of being broadcast to you because you haven't got these big steel barriers in the way, which are going to block those signals from getting to your antenna. So the antenna that I'm talking about is this antenna here, and this is a UHF directional antenna, just so you know what I'm talking about. So this particular type of switchgear, we can't get too close to it due to safety clearances. The ideal spot to test on this would be to do a TEV test down here. So get the TEV device and put it on the outside of these cables here. You would also put it up on top of the bus bars here, but we can't get close to it due to safety clearances. The other test that you would also do is run an ultrasonic test over every single part of this switchgear here to see if you can hear any arcing and sparking and surface activity, corona, that type of stuff. The ideal way to do that test is to get an ultrasonic parabolic dish, such as this one, and stand back 1 or 2 meters away and test the equipment. So the first test we did was we did a TEV test. We did a TEV test around the outside of the switchboard on the outer casing and couldn't find any TEV activity at all. Now that doesn't mean there's no TEV activity there, because we can't get close enough to the switchgear, so that hasn't covered all our bases. The next test we do is that we did on this one here was a UHF test. So what we were able to do was stand about 1 or 2 meters back, point the antenna at the switchgear, play with our settings and tune in to some PD activity that was occurring. So this phase plot here is a phase plot taken from that ring main unit, and what I can see within this phase plot is 2 phases of discharge. First of all, you've got this cluster here, 180 degrees away is another cluster. That'll be a single phase source of PD. Then what we can also see is another cluster here and another cluster here. That'll be a second phase of PD. So I can tell that there's 2 phases of PD occurring by pointing the antenna at it from a couple of meters away. And then the next step is, at that point in time, we don't exactly know whether it's internal void or surface PD, because the UHF antenna will see both defects, basically. That's why you don't know. So then the third test that we ran was we got our parabolic dish, which you can see up here in the right-hand corner, and we stood 1 or 2 meters back, and we were able to sweep that over the whole switchgear, and we could see, or we could hear and see, crackling and arcing and sparking coming from this location here, and also this location here, where you could see white deposits on the outside of those cast resin insulation, basically. Now, when we did that, we could hear the sound. We could also see this phase plot that lines up with the phase plot of the UHF antenna. We could see that here, this phase plot here is telling me that there's 2 phases worth of PD occurring. The first one is here, where we've got this cluster and this cluster lining up with each other. And then the second phase worth of PD is this one here and this one here. So we were able to use those 2 techniques from a safe distance to find PD on the switchgear. In that instance, TEV was not an effective test because we couldn't get close enough to the gear. Okay. Now with the UHF, I said it earlier, when you've got fully enclosed switchgear, it's not the best technique because those signals won't get through that metalwork to you. When you've got open outdoor assets and you've got bushings and all that sort of stuff, the UHF signals tend to emanate from those regions, and they'll get through gaskets and all that sort of stuff on the bushings to get to your antenna as well. So it's a good technique for that. Okay, so in summary, there are multiple types of PD sources that we went through in the start. So you've got the internal, the surface, the corona, and then you've got the gap type discharges and the floating metalwork type discharges. Okay, so all of them have varying levels of importance and severity, and we care about internal void a lot more than we do about floating metalwork. We care a lot more about surface PD than we do about, say, corona in an outdoor yard anyway, because corona has very likely been there since the day you built it, to the day that you're going to turn it off. You have multiple types of HV assets that you guys work on and that you guys manage. So it's good to know what types of PD there are, what types of assets you've got, and then understand what types of defects are going to build up on those assets. And then from there, we have a multiple range of test techniques and equipment available to find those defects. Like the UltraTev Plus 2 can run 4 different tests now. It can run TEV, it can run ultrasonic, it can run your RFCT/HFCT test for your cable PD. It can also, now the UHF directional antenna also plugs into your UltraTev Plus 2. So you can cover 4 test techniques with the one instrument. And then what we want to do is understand what the best techniques are to detect what's going on inside that switchgear, and then apply those and test effectively. Okay, so it will give you an improved asset performance because your assets won't fail, basically. It'll give you greater reliability and safety of those assets, safety of those around it and those working on it. It will lower your costs because you'll spend money where you need to and don't spend money where you don't need to, and that also helps you make smarter investment decisions over time. Okay. Here is our direct contact details. We've got a few questions.
Yeah, if you just want to go through this one.
Yeah, so we've just got a few questions come through on our little webinar thing here. Nice. For a known PD ultrasonic source. Okay, so we've had one here saying, what's your advice for a known PD ultrasonic source? Even with rectification, it still persists and physical inspection shows no apparent surface PD. So in that instance, my thought process would be, could the sound be coming from another chamber? Could the sound be coming from one of the chambers next door or the chamber behind? If there is surface PD occurring, you know, maybe you need to leave it there for a little while and see over time if some sort of degradation is occurring. Yeah, you've really got to track down where that source of PD is coming from, because if you've got sound coming from a surface tracking source, a surface activity source,
there's some form of electrical interaction happening inside that chamber.
Yeah, maybe it's just something that you can't, like you've rectified it, it's still there, but maybe at this point in time there's no physical defect that you can see straight away because there is an interaction happening, and maybe that physical part will become visually more obvious over time. So it's a bit of a tricky one, but yeah, that's the thought process I would be doing.
So it's just going through this now. It's got a whole bunch in quite quickly.
Have we?
Yeah. So that's eliminate EMI from an outdoor environment.
Okay, so how to eliminate electromagnetic interference from an outdoor environment? The short answer is you can't. Yeah, you can't really eliminate it. You can. What you can do is there's 2 things you can do. You can either figure out what it is and try and turn it off. So if it's a mobile phone tower nearby that's giving you electromagnetic interference, ask the phone company if they can turn it off, but that's probably not going to happen. And then other times it can be the atmosphere that's creating electromagnetic interference. So as I said earlier, when everything's misty and humid, you'll have a lot more EMF because you'll have a lot more contact sources and corona sources and all that type of stuff kicking off. And then in the afternoon, it might be a quiet environment. So the time of day that you test may be able to help you diagnose or just help you to test in a quiet environment. The third thing is, what usually happens is you just deal with it. And so what you have to do is test while the EMI is there, the electromagnetic interference is there, and just know where it is. So if you, the biggest one for electromagnetic interference is when you're doing your TEV testing. So when you're doing your TEV testing in an outdoor yard, if you go out and take your first TEV test on the first circuit breaker in the yard, and you find that all the readings are 45, 50 decibels, and it's the whole place is lit up like a Christmas tree, I like to say. You've got very high readings everywhere. All that activity will be emanating from something, usually within the yard. Usually it's some sort of gap type issue where sparks are jumping across a gap on your overhead bus. So if you can, what we're doing is emanating those signals out from that source, and it will give you a certain phase plot. So if I click on TEV and then I click on phase plot, that wasn't very well said. what it will give you is that activity will be giving you a certain phase plot. If you can go around and test every single piece of, every single asset in your switchyard, and you see that same phase plot, the closer you get to it, the phase plot will be going up, and then the further away you get from it, the phase plot will be going down. And so it will lead you to where it is. A lot of the time you'll be able to get out your ultrasonic dish, such as this one. If there is a gap type issue, you can point that straight at it and you'll be able to hear the sound from that gap type issue. Another way you can do it is you can scan with your UHF directional antenna, and you can point that at where the contact type issue is, or a lot of time where the signals are coming from, and pinpoint it. And then what you do is you look for differences from that. You keep in mind, righto, there's electromagnetic signals coming from that asset right there. It's swamping the whole yard. I have that in my brain, so I'm going to test everything looking for something different from that, if that makes sense. What else have you got?
Floating metalwork is an issue, basically.
So is floating metalwork, do floating metalwork issues cause potential failure of HV equipment? So do floating metalwork issues cause potential failure of HV equipment? Well, the answer to that is no. You know, like 99% no. I'll never say that it'll never happen. It's just generally when you've got pieces of metal too close to the HV, it's got an induced voltage on it, and it's discharging across other gaps to things of other potential. So it can deteriorate things over time, I'd imagine, but generally we don't find things that have failed because of a floating metalwork type issue. I'll never say that it will never happen, because people in this webinar might have different examples of it actually happening, but in mine and Thomas's experience, we haven't seen it happen. So, okay, TEV can be used for cable head monitoring. The answer to that question is yes. Can you use the TEV technique to monitor for cable head PD? The best way to do it is you'll have your cable head termination up on the pole. You'll have your trifurcation up the very top. The cable will come down the pole. It'll usually sit behind some cable guards, or maybe it doesn't. What you can do is get your TEV device and go up to that cable and take a TEV reading on the cable. At that point, if you are getting TEV signals of concern, if you're getting a phase plot of concern, looks like internal void, you're like, righto, well, it'll either be coming from the termination, something nearby, or maybe even the underground cable near me. So that's when you'd get your Ultra TEV locator. I'll just get that now. The Ultra TEV locator is this device, which you plug into this other device, to the Ultra TEV Plus 2. And what this does is it gives you two TEV plates. One's there and one's there. And what I would do is I would go onto the cable and I would test one up high on the cable, one down low on the cable, and it will tell you whether the PD signals are coming from the overhead or coming from the underground. In this office, we've successfully found a number of cable head termination problems. One of them failed 5 months after we found it and let the client know. You might have seen that case study. I think I put it on LinkedIn maybe a year ago or something like that. Another really good technique to test your cable head terminations is the UHF directional antenna. If you can get this out and point it at your termination and test the termination from a couple of different angles by walking around the cable head pole, you'll be able to tell if there's internal void PD occurring in that termination. All right, what else we got?
Sorry, it's just going down. I'm just talking about this one now. Cable heads.
Typically, we have pilt cable where it seems to be a blind spot at the plumb, which has been scanned the very same day, and it flew on the next day on the same day.
I think we'll get back to that one.
Yeah, we might get back to that one. Determine whether we'll just do another couple of questions and then we'll sign off and measure PD point distance on the cable. Determine whether it is coming internally. Okay, so we've got a question here. High TEV reading. How to determine whether it is internal or external? First of all, if you do a TEV reading and it gives you internal void type patterns, it will be an internal void type issue. The other way to figure out if it's internal or external is to have a listen. So if you scan with your ultrasonic listening devices, if you can hear PD on the outside of the insulation, it'll be an external problem. And generally for internal problems, you just can't hear the PD because the PD is on the inside of the insulation and the sounds from those sparks can't get out to you. Okay.
Sorry, so like number 5 come through.
5 questions. How can you detect online? Okay, so we've got one here. How can you detect online PD for underground cable? That's one's from Dominic. So that one there is one of the case studies that Thomas went through where we put the HFCT around the screens of the cables at the terminations of the cables, at one at each end. And then we can either plug into the UltraTev +2 and detect PD signals, or we get what's called our cable data collector, capture all those PD signals that are bouncing up and down the cable, and then basically analyze that data through software to figure out if PD is on the cable or not. Okay. We've got one here. How do you differentiate for, where's that one? How do you differentiate for feeders with different cable types along the route? PILC to XLPE from Mark. The answer to that one is you can't really. Yeah, you can't differentiate whether you're testing on the PILC or the XLPE. The only way to do that is with your cable records. If you've got good cable records and you know where the paper is and you know where the plastic is, and we get a distance from our test to say, right, there's PD probably here. At that point, you have to say, well, that section is most likely paper or plastic. So you can't tell from the test results.
And then I think final one, just want to go through the location.
And we'll just have one final question. We've got one from Gino. We have PD detected at an air insulated cable box on metal clad switchgear. Could you please repeat how we determine if it's from the cable box or the circuit breaker? So that one there, the PD, it depends how the PD was detected. If it's TEV or ultrasonic, TEV's a bit trickier to find out because, or Gino, could you just answer that and say whether it was TEV or ultrasonic? That'll probably help me. Just type that in, Gino, as another question. Because if it's ultrasonic, the easiest way to figure it out is to, sorry, Thomas, is to use your listening device. You either test the cable box or you test the circuit breaker to listen for sound, and that's how you figure out where it's coming from. But if it is TEV, the first thing that I would do is use an UltraTev locator, and that's where we have the 2 location techniques here. I would test the cable at the rear of the board and make sure the signals are pointing up into the board. I'll make sure it keeps pointing back towards that panel. You can go between the circuit breaker and the cable box itself and see where the signals are relative to that, because if it's in the breaker, this will tell you it's in the breaker as opposed to the cable box. And then probably the next step would be is to do some switching. So if you suspect that the PD is inside the breaker, you would basically open the breaker, rack it out, retest, and see if the signals are gone. As long as you keep the cable box energized, back energized from the rest of the network there. So that's how I would, or how we would do that. Okay.
Other than that, I'm just going through answering the questions we can here, but we've got a lot which I haven't had a chance to get to yet, which we will follow up kind of individually after the webinar has ended. We've just gotten a bit behind. We've got a bit of a flood in towards the end there.
There weren't many questions at the start. We've got like about 20 questions at the end. But that's okay. We will get back to them all.
Yep.
Yeah. Yep. So, is there anything else you wanted to say, Tomo?
No, there are a couple here. A couple I need to get more specifications on for the actual questions.
Yep.
But then other than that, I think that should be us. We're running a little bit over.
Yeah, cool. All right, well, thanks everyone for joining in. It's been great. I hope everyone's learnt a bit. If anyone has any inquiries about the UltraTev +2 or the locator or the UHF directional antenna, or our services that we can provide, 24/7 monitoring, just, you know, flick us an email, and our phone numbers are there. Contact us on LinkedIn, and we will we'll get back to you, and hopefully we can help you out, and hopefully everyone learned some stuff. So thanks for joining in.
Yep. And anyone who we haven't answered any questions, we'll get to you today.
Yep, we'll get back to you.
Yep.
Beautiful.
All right.
Thanks, everyone.
Thank you very much. You go file end.
Which one?
Then you go file end broadcast. End webinar.